Hello there, my name is David Cater. In this video we're going to take a look at how to calculate a circuit in AC that involves an inductor. Here we're going to keep it very simple. It's going to be just a pure inductor, and that's all that will be limiting current. Okay, so just to take a quick analyzation of the circuit, we have a source of 100 volts at 60 hertz. We're in AC, and we have an inductor that is 250 millihenries. So what we want to do is figure out how much current is going to flow in this circuit and how much power, quadrature power, is available in this circuit. So let's go ahead and do that. So in order to figure out what our current limiting property is, we have to figure out what our XL value is. And XL is a 2 pi times the frequency times the value inductance formula. So we just got to do that, 2 pi times F, and that is 60 hertz. And the value of inductance, which in this case is 0.25, which would be 250 milli, and we get a total value of XL of 94.25 ohms. So that's the current limiting effect, is the inductive reactance in this circuit. All right, so what we want to figure out now is how much current is going to flow in that circuit. And it's very similar to DC. We can, in this circuit, use our impedance, and the entire impedance in this circuit is just due to XL. So we could say the I total is equal to our E total divided by our impedance total. And our impedance total, just to state it up here, our Z total is going to equal our XL total because we only have an inductor in this circuit. Okay, so let's go ahead and punch that in. We have 100 volts. And we have a impedance total of 94.25 ohms, and we're going to get a current of 1.06 amps. So even in a circuit with theoretically no resistance at all, in AC, if there's an inductor, we still have a current limiting effect known as XL, and it has reduced us to 1.06 amps. So it's a very substantial effect. Okay, so the next thing we want to do is just figure out what is the power in this circuit. We're not going to have watts because we don't have any resistive load, but we do have another form of power known as quadrature power. So we're going to figure out what is the Q of the inductor, and in this case we have current and we have XL, so we can use the formula I squared times XL, and that's current through the inductor squared times the value of XL. So that's just simply 1.06 squared multiplied by our 94.25, and we get a QXL total of 105.9 volt amp reactive, which is a VAR, the unit of reactive power or quadrature power due to this inductor. So this is a representation of how much power it takes to build a magnetic field. And why it's quadrature power, not watts, is because when that magnetic field collapses, we get a return of that power back to the source. So we don't really lose power until we start to dissipate watts, all right? So that's why we make that distinction. So it's a very straightforward process. Find your XL, 2 pi FL, punch in your numbers, get your current, then use something like I squared times XL to get your quadrature power in the inductive circuit. Now what I want to do is just take a quick look at what happens if we were to go from 60 hertz down to 30 hertz in this circuit. What would happen? Well, if we were to just look at one formula really quick, the ohmic value here is really due to the counter EMF generated by the coil. So the counter EMF is going to be the inductance multiplied by the rate of change of current over the rate of change of time. So why that's important is if I lower the frequency, then the rate of change of current in our sine wave is going to decrease as well. So if I could kind of draw that, here we have 60 hertz and here we have 30 hertz. And so it's a much higher rate of change here than it is over here. That's kind of what we're doing. We're going from 60 cycles per second down to 30 cycles per second. And the rate of change decreases, and so therefore the counter EMF generated by the coil will decrease as well. So if the counter EMF goes down, it's what we want to predict is what will happen to current and therefore the power. All right, so let's go ahead and do a real quick calculation. The XL is once again 2 pi FL, and that will be 2 pi times 30 hertz multiplied by a value of inductance, which is 0.25. And we have a new XL, and it's quite a bit smaller, and that is 47.12 ohms. Okay, great. That's exactly what we expect. Lower frequency, we expect less inductive reactance because we have less counter EMF. Take this idea, and I use a new color here. Let's go ahead and figure out what is the new current that's going to flow once we've reduced the total amount of, the total frequency. So that's going to be E total, which is still 100 volts. Okay, so we're going to assume that we have to make the assumption that our voltage isn't changing, it's just the frequency. And we're going to divide it by our total impedance, which is now 47.12. And we get a new current, which is quite a bit higher, of 2.12 amps. Okay, so that's, of course, we cut the frequency in half from 60 down to 30, and therefore the current doubled. And that's exactly what we expect, because the XL was cut in half. Okay, so definitely easier way to calculate it, just simply multiply it by that change, but we're going to go through this and just kind of prove all of these formulas out. So the last thing we want to do is figure out what happened to power. Current went up, XL went down, so what happened to power? So it's easy to make an assumption, but we want to make sure we know that we're right. Okay, so we're going to look for the Q of XL again, and we said that is I squared of the inductor multiplied by the XL value. So a very powerful effect here is the current squared. So we're going to take our 2.12 amps squared, and we'll multiply it by 47.12 ohms, and we are going to get a new power of 211.78 vars. Okay, so when we're looking at what happened here, we've got to really appreciate the fact that it's I squared times XL. Here, our original vars at 60 hertz was 105 vars. And when we lowered the frequency and therefore increased the current, our vars went up significantly. And why? Because it's all current driven. The amount of flux in this, the amount of flux being produced by that coil is dictated by the amount of current. So if we can increase the amount of current in that circuit, then we can increase the amount of vars that are being developed by this magnetic field. Okay? So really straightforward set of formulas that we want to commit to our memory. XL, 2 pi FL, and then some kind of variation of the power formula. Instead of I squared R, we use I squared times XL, which is current squared times an ohmic value, just like it was with watts, but now we're looking for vars. All right, so I hope you enjoyed this video, and we'll see you in the next one.